We just learned about solving systems of three variable equations using what's called Gaussian elimination to get our system into row echelon form. And before I discuss a couple of other types of unique systems, I want to make sure that we have an understanding, a graphical understanding of what is happening when we're solving three variable systems. So first, it's important to know that an equation that has three variables, x, y, z, the result of that equation is a graph. When we have an equation with just two variables, that produces often a line if it's a linear equation. When we have a linear equation with three variables, we create a plane. And you can think of a plane as being like a sheet of paper that goes on infinitely in all directions. Now, since that's difficult to represent on a piece of paper, obviously, then we can just think of a finite amount of that plane being depicted here. So a plane is the result of graphing a linear equation with three variables. So if we can think about that then, and we know that a solution to a system of equations represents where those graphs are intersecting, what that means for us is that when we have a system of equations in three variables, a unique solution is when all three of those equations or all three of those planes are intersecting at a single point. This is what we know as a consistent independent system. It is consistent because it has a solution, and it's independent because there is a unique solution there. Let me switch over to the other side. Now, when those planes don't ever intersect at all, or I should say, there's never a place where all three of those planes are intersecting, then we say that this system has no solution, which would make it an inconsistent system. Right? So you may have a situation where two of the three equations are intersecting, but you'll never have a point or points where all three of those planes are intersecting. And finally, if we look in the middle column, we see a system that has an infinite number of solutions. We call this a consistent dependent system. And we'll talk a little bit about why this is called dependent in a moment. But this is where all three planes are intersecting together in a line, meaning if we look here, there are an infinite number of points that we can identify that exist on this line where these three planes are intersecting. There are an infinite number of solutions. So for us, we want to be able to find a way of expressing these infinite solutions. So now that we have a sense of what is happening when we are solving a system of equations in three variables, we see that it's an intersection or lack thereof of these three planes. Let's look at a unique type of system, and that is called a non-square system. We call it non-square because the number of equations is not equal to the number of variables. And a system cannot have a unique solution unless the number of equations is greater than or equal to the number of variables. So in these cases, we're going to see that we're going to have a dependent system. So as soon as you see that it's a non-square system, you've got to pretty much rule out the possibility of there being a unique solution. And sometimes we won't know that the system is non-square until we do some row operations. So I actually want to start with number 2, because I think this will be a little bit easier for us to handle as our first jump into working with non-square systems. And then I will leave you to try number 1 on your own, and you can check those solutions in Classroom. But let's look at number 2. So for number 2 here, I see that it's a non-square system right away. So what's nice about a non-square system is I don't have to do a lot of the heavy lifting of showing my row operations. I know that there is no way for me to get this into REF. There's no way for me to get this into row echelon form, so I don't really need to do Gaussian elimination. I can just take the easiest looking equation right now. So for example, 4x minus z is equal to 0, that equation right over there. And if I isolate z, just move z over to the other side, I already see that z is equal to 4x. In other words, x, or I should say z, is dependent on what x is. So this is kind of our first sense of why we call this a dependent system, because we're going to see that these variables, x, y, and z, will all depend on some independent variable. And whichever is your independent variable, we want to call that one, in this case, x is our independent variable, we want to say let x be equal to a. Now let's think about this for a second. Why am I going through the trouble of expressing x in terms of a? Well, a represents a real number, or if I really want to be specific, I can say any real number. And what we're trying to indicate here is that we are going to have a solution, a general solution that expresses this dependent system. And we're saying that for any real number that you plug in, you will be able to get a point that exists on this line of intersection between all the planes. So we're just trying to express here that x is equal to any real number. And so we let x be equal to a. Does it matter which one you set equal to a? Not really. I will say, however, that depending on your system, depending on what you choose, you may make your life a little bit easier or more difficult. So I could have let z be equal to a here. Let me actually just show that. So if z is equal to 4x, and we're saying x is equal to a, then z is equal to 4a. All we're doing is substituting a in for x. Now suppose, and let me just do this in a different color. Suppose I had said, I actually want z to be equal to a. If z is equal to a, then that means 4x is equal to a, then x is equal to a over 4. So I would get a completely different general solution, but it's just another way of expressing the same line. Let me go ahead and just pause this. I'll leave this off to the side for a second. Maybe we'll come back to that. But let's go back to doing this problem as it was. So we know x is our independent variable. We're setting that equal to a. Z is equal to 4a. So all we need to do now is solve for x. And we can say x minus y. Well, y is equal to, well, excuse me, x we already know is a. So we're actually solving for y here, excuse me. So a minus y plus 4 times z, and z we just said was equal to 4a, that's equal to 3. So just to isolate y, we can say y is equal to, let's see, that's a plus 16a, that's 17a minus 3. So we would write our general solution as x is a, y is 17a minus 3, and z is equal to 4a. There is my general solution. This is a way for us to find any given point. This is a way of showing the line that contains all those infinite solutions. So this is my general solution. Now, suppose I wanted to find a unique solution or a specific unique solution or specific solution, I should probably say. That's basically saying, remember what we're saying here. We can plug in any value for a to get a point on this line. So let's plug in a value for a. And I always say, just go with the easiest value that you could think of, which would be root 34. I'm just kidding. You should set a equal to 0. That's the easiest thing that we can do here. When a is equal to 0, y is equal to negative 3, and z is equal to 0. So there is a unique solution that exists on this point, on this line, I should say. For whatever real number that you plug in, you would get a different point. Now to go back, for those of you who wanted to use a different value for a, let's say, for example, those of you who wanted to say z, you wanted z to be equal to a. So let's just finish that up. What would that look like? Well, this is going to make my life a little bit more annoying, but if I said I want z to be equal to a, going back to my original equation, a over 4 minus y plus 4z, which is 4a, is equal to 3. In this case now, y is equal to a over 4 plus 16a over 4 minus 3. So y is equal to 17a over 4 minus 3. So what would this general solution look like? This would be 1/4 a, or a over 4, 17a over 4 minus 3, and then this last one would be 4a. Oh, no, excuse me, that would just be a. There we go. Make that a. So this would be another way of expressing that same line. Now, if you compare the two, you might be tempted to just multiply everything here by 4 and think you can get the same general solution, but you'll notice that this constant then will be off. So I'd encourage you not to do that. So that's one way of solving that non-square system. We're just being able to express our general solution in terms of some real number because it is a dependent solution. I want to do one more example with you. I'll just do this in a slightly different color. I want to do one more example with you. And this is from 731. This was one of the problems that was on your note page, which I didn't get to, but let me go ahead and model this one for you, or work this one out. So here, at first glance, we don't know whether or not it's a non-square system. So I'm going to have to do some row operations, which, by the way, I'm going to call this here my first row. I'm going to call this my second row and my third row. So I'm just going to label that as such. So I'm going to write down my second row from the first step, and I'm going to make that my new first row. So now that I labeled this as my first row, how do I get rid of, well, actually, let's just write it out first because I don't want to confuse anyone. Okay, so now that we have that, all right. So I'm going to write it down one more time. And this previous step was completely optional. I just didn't want to lose anyone. So my first step is to eliminate that 3x. So how do I get rid of that 3x? I'm going to go -3 times row 1 plus row 2. So that's going to get rid of that first value. That's then going to give me -5y. And I'm going to do this in my head, and we'll see if this works. That's going to give me plus 10z is equal to -8. Next, I want to eliminate this 2x term. So I'm going to multiply -2 times row 1 plus row 3. And let's see, that's going to give me -5y plus 10z is equal to +2. Now, I'm going to continue on. And I'm going to worry about that -5y later. I want to clean up my row 3 first before I get to that. So I notice that I have the same coefficients in each of these terms because my next goal is to try to eliminate this term. So I'm just going to go row 2, -1 times row 2 plus row 3. In other words, row 3 minus row 2. Now, watch what happens when I do that. When I take this row and I multiply by -1, I know my y terms are going to get eliminated, but in the process, also my z terms are eliminated. And then now here on this other side, I'm left with 10. And the last time I checked, 0 is not equal to 10. So what does this mean for us? This means we have no real solution. There is never a line or a point or any place where all three of these equations will intersect. So we have no real solution. And if I wanted to classify the system, we'd call this, it's an inconsistent system. So hopefully in this video, you now see how we actually solve a system and how to express our answer when we get to something like this. And we see that there's no real solution. And also going back up, how to solve a system that is non-square and expressing our answer as a general solution.